what it would take to get a magnetosphere back on Mars, which would be essentially reheating the core of a planet, which we can't do. So.
I just saw a trailer for Titan. Have you heard about the movie? I didn't know what it was either, but apparently Earth is becoming inhabitable, so they're making like superhuman, in the army, being able to be underwater, I think. They're like injecting them with stuff. And so in the trailer, he can like hold his breath for 45 minutes and then he turns into like a fish or something.
It's a logical
I don't know.
progression.
It looks really
You
cool.
train to be a Navy SEAL and then become a fish.
Become a Navy SEAL. And then, yeah, and then like,
Yeah.
I don't know. It seems like a good movie.
Crazy.
I wanna
Like, I
watch
can
it.
hold my breath for like 30 seconds underwater. It's like,
In a previous life, I was a water
They're pretty savage.
way far above what humans should be.
Yeah, I'm not.
Pretty cool. It's cool to know that they're there, that they're real people. That you can do crazy stuff with them. And have to do it.
Well, a lot of people could, I wouldn't say every person could become like that, but in their own research,
Oh, it
they
takes-
just don't.
Yeah, it takes a certain person.
Yeah, you have to push all of your limits. Seen G.I. Jane. I loved that movie growing up. It's actually so cool.
Right. Last time we looked at some hypothesis testing with randomization. Now we're going to go through some more of those formulas to do things. So with hypothesis tests about a mean, the kind of big picture is that we have some population, and there's some unknown mean that we'd like to know about, and we take our sample and get X bar, and instead of making a confidence interval, we're going to have some hypotheses that are of interest to us. We're going to have some hypotheses about this mean, and we're going to use the sample along with its sampling distribution to try to evaluate whether the hypothesis seems reasonable. So we're going to set up some hypotheses. The hypotheses, the null hypothesis would be stated that the mean is some value. Usually the null hypothesis means no change or no difference. Everything's just the general population, the status quo. Nothing unusual has happened. And the alternative, one form of the alternative is that it's no longer that case, that there has been a difference. Change from whatever that mu sub 0 value would be. Maybe this is a special subgroup, maybe things have changed in terms of a process, maybe you're doing things differently, just for some reason it's changed. And we're trying to really convince people that it is different based on our data. And so we're going to have this picture. So here's a distribution centered at mu sub 0. So under the null hypothesis, the mean is here. X bar, our sample average, should be approximately normally distributed, by the central limit theorem. So even if our measurements X themselves are not exactly normal, they're skewed or have outliers or something. Once we average enough together, the sampling distribution is roughly normal. And if the null hypothesis is true, then the values of X bar should be kind of close to that somewhere, plus or minus, right? And so we're going to reject the null hypothesis. We would think that this is not so believable, that the mean is this value, if X bar is far from the center, where the null hypothesis says it should be. So if we get out here far enough away from that, based on a reasonable sized sample, we're going to say, wait a minute, the X bar is supposed to be close to here, but we're not here. And that just doesn't seem right. So we don't believe it anymore, that there must be probably another explanation, some other difference going on. Maybe to the sample and there's bias, whatever the reason is, there's some reason that this is not looking realistic. So how far away do you have to be? Well, we set up some standards. So an alpha equals 0.5 significance level. Will mean that we'll reject the H bar, reject the null hypothesis if our average is out in kind of the 5% extremes. If it's set up as two-sided, right, so that the alternative is that mu does not equal mu sub 0, we're going to reject the null hypothesis if x bar is at or beyond the 0.025 tail cutoff. So with 5%, this standard of significance, we're going to look at that graph and find the points that have 0.025 tails under the probability distribution. And if x bar gets beyond those, right, then that's going to be judged to be unusual at a kind of a 5% level. 2.5% that way or 2.5% that way is extreme. Under the sampling distribution is something we wouldn't really expect to happen that often.
Can you scroll down a little
Yeah.
bit?
So we're rejecting the hypothesis if x bar is beyond that. If we, that area where we reject is referred to as the rejection region. What values of x bar lead us to reject the hypothesis? So if we know sigma, and we can use the normal distribution, and large samples, x bar should be roughly normally distributed. We get a picture here, let's redraw the same picture. Here's mu sub 0. This is the values of x bar. And if this is the 0.025 tail here, this out here is called the rejection region. It's actually two pieces of it. It's also the rejection region. And if sigma is known, if we know that, then we're using a normal. So z values. Right. This point out here, that would mean we reject the null hypothesis H0 if x bar is bigger than the mean plus 2 standard errors, plus 1.96 standard errors. Mu sub 0 plus 1.96 sigma over the first band. Or, right, this other way, 1.96 standard errors that way. Or x bar is less than mu sub 0 minus 1.96 sigma over the square root of n. And so we use the relative areas of the normal to set those cutoffs, 1.96 times the standard errors. So that becomes a decision rule. Right? So if you actually see an x bar, you know sigma based on your sample size, sets that many standard errors away, you reject. Now if you don't know sigma, we're going to replace this 1.96 from a normal by a t-value. So it's going to be more like 2, 2.02, something like that. So because the t has more variability, we don't reject quite as much, so it has a little bit more. So this translates into S is used as an estimate of sigma. The t distribution, and this rule is going to turn into reject the null hypothesis if x bar is greater than our mu sub 0 plus a t value. And in minus 1 degrees of freedom. And the book refers to that as the upper 0.025 tail. Right? So there's columns on the T chart, and one of them was 0.025. Right? And so at that upper 0.025 tail refers to that. It's a value about 2, it could be 1.98, 2, but with small sample sizes, it's a bigger value. Times S over the square root of n. Or if x bar is less than mu sub 0. Minus that same value. So that makes a compensation for maybe estimating that standard deviation from the data rather than knowing it in some external way. So if it's out there, it's in the rejection region, and you reject. We call this the alpha level significance, 5% significance in this case, because that value is chosen because there's a chance you make an error. And the significance level is the chance of making an error of rejecting the null hypothesis when you shouldn't. Yep.
That 0.025, is that a part of a subscript of n-1, or is that multiplying?
That's kind of the subscript of the t. So the t value is n-1 degrees of freedom, and it's the 0.025 tail. So you got to put both things.
Okay. Yeah.
We'll do a numerical example
To find the t value.
to look at that t value, yes, because you got to get the n-1 the degree of freedom row and then the 0.025 column. Yep.
So because you're using t-values here instead of like normal z, would you necessarily change your alpha? Would people most likely change the alpha to reflect that, or would it be still that 0.5?
Yeah, probably still the 0.05. Yep. So the change that happens when you're using S is you boost this t. The t is a little bit wider, so it forces you to have a little stronger evidence.
Okay.
Because there's extra variability just in that. Yeah.
Is there like a formula for S?
S is the sample standard deviation.
Oh.
So that will be from just the data values that we get. So this alpha, to put, is the statistical significance level. It's referred to as the probability of a type 1 error. It's the probability that you reject the null hypothesis if the null hypothesis is true. And we don't want to do that very much, right? So we usually set that rule about 0.05 or something like that. 0.05 would be kind of a standard. Sometimes people use 0.01, sometimes people use 0.10, but it's usually a small value. Yep.
Just to make sure, be crystal clear, rejecting HO if HO is true, that's saying that you're rejecting, saying that there's no difference.
Right.
When there is in fact no difference.
That's right. When you're rejecting it, it means you're saying, yes, there is a difference.
When there is not an actual
There is
difference.
none. So if we have these null hypotheses, if H0 is true, that means that the sampling distribution of x bar truly is centered here at mu sub 0. And the x bars you see should be pretty close, right? On average, they should be a little bit above.
Yes, spilled the coffee.
Oh.
Oh no.
Recurring.
Recurring tragedy. All right. So if it is true, we would expect, our x bars to be pretty close there. And so we're not going to be in the rejection region. We're not going to be out in the tails, right? But 5% of the time, we do land in the tails, right? And we do make that error occasionally. Yeah.
All right, so I'm just trying to make sure this is crystal clear for my brain. So the distributions that we're using are the normal or the t distribution, correct?
Mhm.
Okay, just making sure. And then
And the alpha interpretation as 0.05, whether you're using t or normal, it has basically the same interpretation. There's a 5% chance, 0.025 here and 0.025 here if it's split evenly, whether you use normal or t. And there's a 5% chance you end up in one of those rejection regions, even if this is really the truth. Right? And so that's an error. So we don't want to make that error too much, and so usually we choose about 5%.
So, also just to be clear, so you get the alpha, the mean that you're working with from your state, or the standard deviation from the sample that you're given, not like a bootstrap sort of idea, right?
That would probably be the typical way, but in our formulas here, we have, right, S over the square root of n, that's kind of a standard error, right, this thing. Standard error. So instead of using S over the square root of n, if you had used a bootstrap, you'd get a standard error there, and it's still, you're going to reject the null hypothesis if the average is more than about 2 standard errors away
Okay,
from the center.
thank you.
Yep. So,
Hopefully I didn't set it back too much, just
oh,
want
no,
to
no,
make
no,
sure.
no, no, I think we're gonna look at an example. And so this is based on 8.14 in the book. And so, this is looking at cars and braking distance at 40 miles per hour. How long does it take them to stop? Current brakes, current braking systems, stop in 120 feet. Just don't stop immediately. Takes a lot longer on ice too. And then there's new technology. And we can ask, is it better? Which translate is stopping distance smaller. Well, is it better would be stopping distance shorter. Another way the alternative might be phrased is it different? Sometimes you ask the question, you come up with a cheaper way to make the brakes, or you've altered something in the production process, or now you're getting a part from another country that you were making in the United States before, or something. So you've changed something. And then the basic question might be, is it different? Not necessarily that it's better, just is that you make this change. So is stopping distance different? And let's say we do, we have 36 cars, 36 repetitions of this process. The average stopping distance for these 13 is 117.2. And let's assume that the standard deviation of stopping distances is 10 feet. Now, 10 feet might be something that would come from the thousands and thousands of trials on the standard technology. Maybe it applies to this one. Let's pretend you're doing that number right now. Based on this, do we reject 120 feet as no longer realistic? So to do these things, we're setting up a null hypothesis and an alternative hypothesis. If we're doing first the one that is it different? Let's do this one. Do this one first over here.
The HO would be that it's not different.
Right, that's not different, so what value is that?
So it would be like around 120.
Yeah. So the null hypothesis is going to be 120 feet. Right, it's still the same as the old cars. We say that it's just, is it different? We change some part in there, is it performing like it was before? Right, that is just that it's not, the alternative is that it's just not. Do we reject? Right. Well, we reject if our average is less than 120, right, minus our standard error. Now, if we're using normals, right, for this, we would put in 1.96, right? And so this is two-sided, right, because this, so we take the alpha 0.05 if that's our standard, divide it into 2, and so we're going to use that number there, and then standard error, so sigma over square root of n. So 10 over the square root of 36. And that number ends up being 116.7 feet. If it's two-sided, so we really would have we would reject if it's greater than 120 plus 1.96 times 10 over the square root of 36, which comes out to be 123, 127.3 feet. And so if our data is 117, are we going to reject 120? No, we're not going to reject it. This is a picture where we have, 120 and 117 is something, 17.2 is something like this. And then our rejections are a little bit further out there. So 116.7 is where we would reject 120 or up here. And we're not quite that far out. So at the 5% significance level, we don't reject. Things could still be the same. Any questions? Now, sometimes we do a one-sided, where we only care about one direction, right? And we only do tails in one direction. Yeah.
So what, I know that alpha equals 0.05 is the standard, but what makes you choose that compared to 0.01, for instance, or 0.1?
So we'll talk about an
Okay.
example.
Sorry.
No, that's fine, right? So it's kind of the context of the problem. So let's look at the second one up here, really. Is it better? Right? So these one-sided things, one-sided, is average stopping distance shorter? Null hypothesis is still the same. The old average was 120, no change from that. When it's this one-sided, like you really believe, you're really only interested in changing the technology, to make it better, then it's less than 120. So in this picture, the picture changes a little bit for these one-sided ones. U sub 0 of 120 is still here in the middle. This is the sampling distribution of x bar. And now we're going to reject only if it's in the direction we hope it's in the good direction. Right? So we're going to reject down here. We're not going to use a rejection region on the other side because we just don't believe that it's ever going to happen. If it ever did happen, it would be ridiculous, right? So it would be no use to us at all. So at alpha equal 0.05, we put all 5% down on one side. And if it's out in that 5% tail, then we're going to reject. So we reject if x bar is less than mu sub 0 minus some z value times sigma over the square root of n. At 5% with one-sided, we need to use a different z value. 1.96 with zero would be at 2.5% on both sides. You'd be looking at the standard normal, centered here at 0, about 1.645. Has about 5% down here in this tail. Right? It's not quite as far away as 2.5%, which is 1.96. And right. So there's a minus here, but this is the subtracting 1.96. So we were 120 minus 1.645. This was 10 over the square root of 36. So now we're going to reject if it's less than that, right? But one-sided, where's my one-sided? There it is 117.3 feet.
So what was our x bar again?
X bar was 117.2.
Oh my god.
Right, so it's pretty close. Right? But it's less than that. It's just a little bit less. So in this, the cutoff is 120, here's 117.3, and we landed, boom, just inside the rejection range. So a 5% test, one-sided, you would reject, right? Is that logic? Yeah.
So what if it's exactly the same?
Well, I think about it as a matter of communication, right? Is that it's best, well, whenever you communicate these things, well, you have to tell people, are you doing a one-sided or two-sided test? Right? So that you can, this is a two-sided test, this is one-sided, like one tail area, or two-sided calculation, right? You tell them what you're reporting, right? How you're doing it. And then people have to judge, was there a reasonable expectation that you would really get that one-sided thing? Right? Did you plan on that? Or you get some obvious advantages from doing one-sided because you get to use 1.645 instead of 1.96. Right? Things that weren't significant when it's two-sided can be significant one-sided. But if you look at your data and say, oh, I'm going to go that way, that's kind of cheating a little bit, right? It's kind of like peeking at the answer and then saying, oh, I really wanted to do that. Right? But that doesn't really fly. People are skeptical about that. So in medicine anyway, clinical trials that are done to prove whether the drug's done get registered. And the hypotheses get stated up front. Right? And then they report whether they're doing one-sided or two-sided things. And then people can judge, was that, they usually state a primary outcome. We think that this is going to reduce cholesterol or blood pressure or the rate of resurgence of cancer or something. So they state clearly that we think it's going to go this direction. Based on this evidence, we're making this. Now we're going to do our trial, and we're going to test with a one-sided hypothesis. Right, there's a website called clinicaltrials.gov that lists trials that are registered. And to get the results of trials published in New England Journal of Medicine or the Lancet or other top journals, they ask, did you register your trial? If you didn't register your trial, they say, you can't publish in our journal. You didn't follow the rules. You didn't state clearly what you're going to do, and you might be gaming the system. So one-sided are often used and totally relevant for problems, but generally they need to be justified. Take that because this is so if they really did improve technology and it was really aimed at improving the case, and maybe they've done a few tests on a few individual cars to see if it's kind of working. They run it on a machine that doesn't involve a driver and it's closed track, and just in the lab they can run it and it looks like it works. And then they make a claim that it's going to lower it. Then they could do this one-sided, and they could reject. So it looks shorter, looks better. Right? So they could market it as possibly better. But any questions about? Yes. No. Yeah.
This is one that's like, for most studies and things, the p-value, at least for published works for the general public, you don't usually see these p-values and things. Do you, for advertisements of this drink will make you feel better, or will do this sort of things, is this the sort of study that has to be done to be able to justify that?
Well, so some things, if it's really clinical, right, and claiming that there's a medical benefit, right, it's usually they have to do some type of clinical trial, some type of study like that to do it. Marketing things, just saying that there's kind of looser standards.
Mm-hmm.
So I don't think all marketing research has quite the same standards of registering things. It's a little more exploratory, so it probably has to take a little more grain of salt. But yeah.
I know there's been problems in the past with that, with Sonic energy drinks. They were saying that it increased your ability, your brain power or something like that, and there's actually a lawsuit about it. So.
Yep. Right. Yep. So there's organizations. Actually, my brother's a lawyer for Pharma, which is a pharmaceutical association in DC. One thing they monitor is these claims, right? There were some products claiming that bee pollen would solve all these diseases, right? But there's no clinical studies, no rigorous evidence that was true. So the association, on behalf of the big pharma companies, went after these individuals. Said, you can't put that on a product. You haven't proven it, right? So there is some regulation on that. So in this problem, most likely sigma would not be known. You wouldn't want to trust that it's still that. Let's say that instead, so we have our n equals 36. The average stopping time is 117.2, And so let's say that the sample standard deviation is 10 feet. So this is the sample standard deviation based on the 36 measurements. So once that's based on the data, we're going to, maybe that 10 feet is it's a low estimate, maybe it's a high estimate, but it adds this extra bit of uncertainty. So we're going to use the t-distribution. The degrees of freedom is going to be 35. We used up one thing we've estimated. We're estimating the mean, so there's one more degree of freedom. The 0.025 tail for this one occurs at about 2.03. So under this t-distribution, the one is centered at 0 for a t35. The one that has the 0.025 tail, looking at the charts, is about 2.03. The 5% tail, if we're thinking about a one-sided thing, is a little bit is lower, just like it was for the normal. And so if you look under the 0.05 column for that one, that is about 1.69 instead of being 1.645, 1.69. So it's a little bit bigger, right? So yeah, because you're estimating that standard deviation, to be convincing, you need to be a little bit further away. Right? So let's say what happens. So if the null hypothesis is that it's 120, and the alternative is that it's not equal to 120, we're going to reject, in this case, reject the null hypothesis. If x bar is bigger than 120 plus the t-value, which is 2.03, and then the standard deviation, which was 10 over the square root of 36. Or x bar is smaller than minus 2.03, 10 over the square root of 36. And we didn't reject when it was 1.96. And now with this change, we're also not going to reject. Do I have those? I don't have those particular values, but I know that we don't reject here because we didn't reject 1.96, so we're not going to reject. Right, x bar was 117. Is not outside of those things. Right? But but it's one-sided, and we make the case that we really believe it's less than 120. Right? Then we reject the null hypothesis if x bar is less than the 120 minus, now we use that one-sided t-value, 1.69, 10 over the square root of 36. And this one is 117.2, 180. Carry a couple more decimal places, and it's like that. We rejected all hypotheses if x bar is less than that. Yeah.
Just to give you values for the other one, in case you wanted them.
Sure.
It's going to be 123.3 for the top one, or 116.16. Or I'm sorry, just 6. 0.6, not 1.6.
Right. So the 117 is not bigger than that, and it's not less than that, so we don't reject for that one. This one-sided one, right? Here's the 120, and we're going to reject if it's less than 117.8. This is where we reject the null hypothesis out here. This is a 5% area for the one-sided.
Well, hold on. It's 0.18.
1.8, sorry, yeah.
Sorry.
Thank you.
No, it didn't. Sorry.
That doesn't matter, because our mean of 117.2 is just right there. It just failed barely. Right? So if you did this one, even with this one-sided thing, you're not going to reject and not get conclusive evidence that it's less than 120. It certainly looks like it. It's pretty close to that boundary. But if you want to maintain this 5% significance level, you don't want to make more than 5% errors, this thing is not quite far enough out. So it could be viewed as unfortunate, that doesn't quite pass. Right? If you're really going to stick to that 5% as your only deciding, your deciding criteria, you're not going to budge on that. It doesn't quite go beyond that.
And you wouldn't just round that up either, right? Just make it equal to that.
Right, so yeah, so if you rounded it, it's going to be very close, but it would be kind of right at the boundary, but you couldn't really say that it's less than that, right? So, but that doesn't seem to, so that would be the conclusion, right? If you really wanted this 5%, this one would not reject either, right, as well. So do not reject. That the mean could be 120. You have something that's somewhat unusual, but not quite at that 5% level. Right. So one of the ways these things get reported is by p-values. So instead of saying it's more than 5% or less than 5%, you could give the actual probability, right? Instead of saying, well, it's not quite in the this 5% scale, we could say, well, where is it? It might be 0.501, 0.0501, just a little bit more than 5%. And therefore, we would not reject. So p-value is the probability of getting results as extreme or more so than the actual result. If the null hypothesis is true. So it's kind of a mouthful. And so the way we quantify these is by looking at tail areas, the probability you're at your x bar or beyond under the null hypothesis. So under the null hypothesis, mu equals mu sub 0. Here's the sampling distribution of mu sub 0. I'm sorry, of x bar. And if we get an x bar up here, this is our actual number. There. The tail area, so this is this picture, right, illustrates the sampling distribution of x bar in samples from whatever population it is of size n. And the probability of being at x bar or beyond under that distribution is a tail area. So this area here, right, is the tail area probability. And either that is a p-value or we double it for a p-value if it's a two-sided alternative. So if we're looking at an alternative hypothesis, in this case, it says no, the mean should be bigger than our value, right? Then that tail area is called our p-value. And if our p-value is less than 5%, right, less than whatever alpha significance level we want, then we reject. If the p-value is less than or equal to alpha, about like 5%, then we reject the null hypothesis. And the p-value then is something you can tell people. We rejected it and the p-value was 0.023. Or we rejected it and the p-value was 0.049. So they can know exactly how close you came to that 5% boundary. Yeah.
Isn't also the p-value something you have to announce before you start your experiment with any clinical trials as well?
Well, so not necessarily the p-value, the p-value really is computed after
No, not
the
the
fact.
p-value, but like your significance levels.
Yeah, usually things are planned, right? So alpha, kind of like a confidence interval. Where you say you're going to do 95% confidence intervals. Well, we're going to do a 5% significance. Usually you state that up front. Usually that's not too controversial because it's usually just kind of a standard thing. Right? If you try to deviate much and say I'm going to use 80% or something, or 99.9, people will raise a question, why are you doing that? Why are you being so different from 95? If the alternative, though, you know, in this example, had been that it's simply not equal to that, right? What's as extreme or more extreme, right? Well, that's the same, right? At this or beyond. But if you think about it symmetrically, and it's just not equal, right? Then anything equally low or beyond, and then the p-value gets doubled. So the alternative had been just that the mean is not equal to mu sub 0, right? Then the p-value, right, is 2 times the tail area probability. And a small p-value means that you reject, right? And if your goal is to reject and prove that something is different, right? Generally you want small p-values. So if you really can set things up to do one-sided tests and really justify that before you gather any data and start doing things, you have an advantage of doing that. But it's a matter of communication, right? If you say, I got a p-value of 0.04, people are going to say, is that one-sided or two-sided? Did you plan that before, or where was the document that stated what your primary hypotheses were? Right? How do you justify using one-sided versus two-sided? When did you state that? Was it after looking at the data, or did you do research and establish it in a convincing way before? Right? So let's do this example with this one, right? So we could say we have our 36 observations. If we have sigma known, right, so we use the normals, and x bar is 117.2. If we have a null hypothesis that mean is 120, we're going to calculate a tail area. So here's the x bar distribution. Here's 120. We get a 117.2 here. We want to calculate the probability. We're out this way. Right? And that's going to be our tail area. So our tail area, if it's using a z, we're going to do z equals, we're going to standardize things, our x bar minus the mu sub 0. And we're going to divide by the standard error. So sigma over the square root of n. To calculate areas under normal, we always z-scored things, and so this is the z-score process. So 117.2 minus 120 over 10 divided by the square root of 36. So that z-score ends up being negative 1.68. The area under a normal curve under a standard normal less than or equal to the negative 1.68 is 0.0465. So if we wanted to do a one-sided test, right, that is lower, I really believe that before. So the alternative is that the average really is less than 120. Our p-value then is 0.0465, which is less than a standard cutoff of 5%. It's out further than 5% of the results. Right? Because that's small, we reject the null hypothesis. If, on the other hand, you didn't have that, and you're in this scenario where you just changed a part or got it from a different manufacturer, use some different materials of some sort. Right? And your alternative was that it's just not equal to 120. Well, evidence could be 117.2, or you could be that far above, and it'd be equally likely to be equally kind of inconsistent with the 120. Right, then our p-value, you double it. That's the calculation. So it's 0.093, which is bigger than 5%. And so if that was the case, right, 10% is not as unusual as 5%, so then we do not reject. H0 at the alpha equals 0.05 significance level. It doesn't pass that standard. If we replaced, if we really didn't think this was sigma, but based on the 36 observations itself, and this was S, we'd have to use this t distribution. It's the same standardization, but with S put in there. But you have to use a t distribution to get areas instead of normals. So if n is 36, x bar is 120, standard deviation is 10. This is based on the sample. No, sorry, x bar is 117.2. The null hypothesis is 120. And let's do this one that says that it's less than 120. We standardize x bar minus mu sub 0 divided by standard error. Right, that's what we're doing. X bar minus mu sub 0 s over the square root of n. So 117.2 minus 120 over 10 over the square root of 36. And that's the same value as before. It's still negative 1.68. I haven't changed any of the values. But now we look at a t distribution with 35 degrees of freedom, which is a little bit wider. It's a little bit wider, has a bigger chance of having extreme values. So it's going to have a little more probability on the tails. Right? So our evidence with the t isn't going to be quite as convincing. But it's better in terms of actually having a 5% chance of that type 1 error. But we'll talk more about the interpretation of confidence intervals and this alpha and things. So the probability that a t35 random variable is less than or equal to negative 1.68. If you look it up on the computer, is about 0.0509. Right? And if our alternative is one-sided, which is an alternative that is less than 120, our p-value, that tail area is our p-value. And that's a little bit bigger than the 0.05, and therefore we do not reject the null hypothesis at that 5% significance level. It just doesn't quite make it. Right? With the t. And that's probably a little more realistic than using the normal. But I'd rather know the p-value. Right? I'd like to know 0.0509 or 0.051 and know that the difference was 120 versus 117 feet. There's about a 3-foot difference. Right? I'd rather know that information than just saying it wasn't significant. Saying that it failed to meet 5%. I'd like to know this number to say, well, now I understand that it's very, very close. I also see that there's only 36 cars, tests. Right? We'll talk about what affects things. Right? But in the denominator, here's the standard error, s over the square root of n. Right? If that had been 360 tests, so you have 10 over the square root of 360. That would make this statistic a lot bigger. Right? So if you doubled, quadrupled sample size, and we still got 117 or something even near that, right, then that's very significant. 36 might be a, you know, smallish sample size. So that if I know that the p-value is like right about the 0.05 level, but it's based on a pretty small sample size, and they're telling me the engineers have done things to make the car work better, I think, well, you know, I'm not totally willing to give up on this yet. It might be worth a little more testing to see if, with a bigger sample size, other different conditions, etc., it doesn't make a difference. You might want to test these cars at 50 miles per hour or 30 miles per hour as well, and see if it's more convincing at that speed. Maybe this new braking technology works better at 60 miles an hour and above, and makes more of a difference. And you see smaller impact of the change at this lower. So you know, there's a lot of ways that this could still be used, and testing and hypotheses are usually never. You know, there's a sense in which some things are yes or no. Is this new drug better or not? Can you approve it? There's kind of this decision, but in really scientifically trying to understand things, there's a little more gradation. You kind of want to know a few more details. So communication, I would say that give the p-value, give x bars, you know, one-sided versus two-sided, estimate standard errors, you know, give the whole works, and you know more about what's going on. A graph of the data would be kind of nice, which is 36 observations. If one car kind of slid off the tracks or totally missed the mark and went 200 feet, and there's a big outlier out there, that's going to kind of distort everything. So you kind of want to know what the data look like too for interpretation. But any questions? Right? So let's do one more numerical example just to get a few new numbers. Another book that's used in a class like this is Nuvidi and Friedman, I forgot. But it's their problem 6.9 in their book. Right? And so this is looking at profit performance on international construction projects. This is actually from an article. Authors are Han, Kim, and Kim, 2002. It's a journal of concrete engineering and management science. Concrete and building things with dams and bridges and roads and buildings is just enormous as an industry. There's a journal that looks at scientific things about managing that process. I've never seen it, but it's quoted in the article. They had 126 projects they looked at. The average profit was 8.24%. The standard deviation of those percentages was 16.33%. And the question they asked, is the profit significantly different from 10%? Set up as the null hypothesis.
So different or lower, significantly lower than, I guess is the question.
I think that there was just setting, so I'm imagining a scenario where they set up that they hope to make 10% profits. So they're aiming for 10% profits, and they have it, it's not kind of a randomized study where they think it's going to be one way or the other. They're just asking, is it 10% or not?
Right, so the HO would be that it's equal to 10%.
Yep.
And the HA would be simply not equal to 10%.
Right. So you could find where you reject and see is this in a range that you reject, or you can find the test statistic by taking the t-value and then comparing that to a t-distribution, or you can find the p-value. So there's kind of a few ways of looking at it. The t-statistic, and I haven't called it that before, but when we take the data and standardize it, and so is the square root of n. It's a statistic, it's a function of our data. Mu sub 0 is known, so that's a number. So the average was 8.24. The comparison number under the null is 10. Standard deviation is 16.33, and there are 126 projects they got data on. So to calculate that, that's negative 1.21. Based on that, we already know something, right? Are we going to reject the null hypothesis? Here's a t-value of negative 1.21. Is that very far out? Or it's not at 0, but it's not 2. It's not negative 2. So a t distribution, we want to look at the one that has 125 degrees of freedom. The 0.025 cutoff for that thing is about 1.98. A little bit bigger than the 1.96. So we look at positive 1.98 or negative 1.98, and this is not that far out. Right, so we do not reject. Reject H0. 10% could be a plausible value. Your best estimate is probably 8.24 for projects like this, but 10% is not completely, in the sample, however they sample these projects. It could have been 10%, and you could reasonably get something about this size. Yeah.
So the t-value is 1.98, like what would be, like what's the cutoff, like what would be?
Right, so the t statistic from our data is this negative 1.21. So if we have a t distribution here with 125 degrees of freedom, the tails, the 2.5% tails are 1.98. And negative of that because of symmetry. Right? And our data ended up being negative 1.21. So we would reject 10% if we were out in the tails. Those would be our rejection region. But we're not there for actual data. Actual data t-value is here. Sometimes these cutoffs out here are called critical values.
Alright, so we know that that we rejected because it's not at negative
98 or below, right?
Okay.
So do not reject. In this case, the average was 10% we were talking about. The tail area, right, it's going to be, if this is 0.025 out here, this one has to be more. The probability that a t distribution with 125 is less than negative 1.21, get that off the computer, is 0.114. Right? And so a two-sided p-value is twice that, right? So 0.228. Not unusual, not less than 5%. Right? More like 1 in 5. That happens all the time. Right? And so with this, right, do not reject. Either the t statistic or converting it to p-value answers the same question, but it could be expressed in do not reject the null hypothesis because it's always hard for me to write it, right? Because the p-value is greater than 0.5.
Can you go back to how you got 0.114? That sound right?
That p-value, right? So it would have to be taken from this table. So the area here to the right under this curve The area under all that is actually 0.114.
Okay, so it's going from.
Our actual value all the way out. But we'll do more interpretation of hypothesis tests and how they relate to confidence intervals and that stuff on Monday.
Thank you, Professor.
Thank you.
You gonna do anything fun for it?
I'm sure I'll do something. At this point, I don't know. So. A lot's up in the air.
Well, sometimes it's nice to play it by ear too.
Oh yeah, I mean, you play at St. Michael's, there's a potluck at the middle school, and a little dusting of snow, so maybe get outside.
Do you ski?
So, not as much as I'd like. The downhill, and I've done a little bit of cross country, but I'm not very good at that. So. Bye. Thank you very much.
I'm sorry.
Where's the handout from Wednesday?
Thank you. Have a good weekend.
I'm doing a hard reset and then coming back on Monday, so.
Okay.
I'm not gonna talk to you on Monday at some point, I will let you know.
Monday morning's a little bit tight. I have to go talk to Radim about something, but
I can understand that it's being an important issue.
yeah, but so Monday afternoon.
Maybe,
Maybe.
I have a lab, but,
Okay.
Do you think you'd have time to review
But
about
something is probably work out. We can probably meet for a short time on
I'm
Monday
doing a
as
no,
well.
I actually recently learned that I have
So,
ADHD, which is part of
if
the
you
reason
wanna,
that everything has been so difficult for me.
Right, and so that would be maybe.
I'm not done with it today.
Well, when you finish it.
Amplified
just-
stress.
I'm editing,
Yeah,
I already have it
paper
written
now,
out,
I'm just editing it, like doing big thinking about it, it's like, no, I think I'm pushing not too hard. Last week, so like, it's really touching me now, and I'm all through it.
Well, do what you can, if you've done parts of the homework, send those,
Yeah, I'll be missing, somebody out a lot
Oh,
this
yeah.
weekend, going home to work and like getting out of there early on the environment.
Yeah,
Sure,
I-
couple.
Yeah.
This might be,
That's,
Maybe it's fine.
so, yeah.
Okay.
I appreciate it.
Sure.
Appreciate your patience.
Oh.
Thank you so much.
share the paper.
Good morning.
We'll get it done.
So,
Yeah, no, I'm not worried about it.
did you
Okay.
get my email?
Oh, okay, yeah.
It had,
but no,
Mr. Cash, and I
Getting
had
there.
problems
Getting
with
there.
my reply
That's good.
because when I was transferring
Yeah.
into R, I
Yeah.
kept getting 0 for
Okay,
like a whole
something.
bunch of
Yeah,
zeros.
Right.
I don't know if I just like read the directions wrong, but
Maybe we could meet sometime, because I don't think I got any
okay.
email.
I can
about
send it to you right now.
Okay. If you could
Like
try
at
to
least the
try.
homework so that
Yeah, then I could,
my Wi-Fi is very weird in my room.
in the dorm, yeah.
Yeah, in Canterbury, cause I'm all the way at the end, and so
Ah.
it's like, because it's kinda in between buildings, sometimes
Uh-huh.
the connection isn't quite right.
It's always frustrating with technology things, so
Yeah, cause
where
I
you go, what
didn't
you.
put everything in, but I just kept getting whenever I tried to do the,
Okay, it started out with that, but it just seems to have not put any numbers in there, so.
Yeah.
So it has to run the loop. There's a loop, like a 4